Hello everyone, today my presentation is CFMNet, Coarse-to-Fine Cascaded Feature Mapping Network for Hair Attribute Transfer. My name is Zhang Guisong. This is the outline of my presentation, including introduction, method overview, dataset generation, experimental results, conclusions. Introduction. First of all, let me answer the question, what is hair attribute transfer? Hair attribute transfer is to manipulate hair attributes with definite target. The input contains two parts, the source image and the target attribute. Usually, a designed tag of hair is assigned as the target. For example, add bounds to this image. The result is a source image replaced with target hair. There are two kinds of hair transfer methods. One of them is 3D hair model based, and the other is deep learning based. With 3D hair models, we can control every single strand of hair directly. However, it is still a hard work to render 3D models into photorealistic images. For deep learning-based methods, although generated images are photorealistic, we usually can't transfer hair with fine-grained manipulation. Therefore, how to delicately transfer hair and generate photorealistic images becomes the main challenge of our work. Overview. This is a pipeline of our work. To delicately manipulate hair attribute, we propose a coarse-to-fine pipeline for hair attribute transfer. As shown in the upper figure, after embedded to latent space of cell GAN, there are 5 feature mapping subnetworks cascaded to transfer hair attribute. 3 of them in red are coarse-grained feature mapping subnetworks, Cgfms, which transfer attributes of hair length, waviness, and bounce. 2 of them in green are fine-grained feature mapping subnetworks, Cgfms, to manipulate hair attribute with 3D geometry and 3D color. The bottom left is detailed method of Cgfm. We extract facial identity with identity extraction module, IDEM, and hair label with label extraction module, LEM, from latent space. We then apply iterative mapping with identity loss and label loss. Similarly, in the Cgfm, we extract 3D hair model from latent space with hair extraction module, HEM, and then optimize the portrait with identity loss and hair loss. This is the architecture of pre-trained LEM, IDEM, and HEM. The input is embedded portrait in latent space. In first 2 figures of LEM and IDEM, the output is binary label, or identity feature. So we take multi-layer perceptron as backbone. For HEM, the output is 3D hair model with 1,000 strands of hair. So we extract hair model with the deconvolutional networks. The third figure is color part of HEM, and the fourth is the geometry part of HEM. We chose coarse entropy for label loss in LEM, L2 norm for hair loss in HEM, and the cosine value for identity loss in IDEM. We divide the transfer process into 5 subnetworks corresponding to each attribute. In the equations, all signs for hair attribute of loss, waviness, bounce, geometry, or color. Li, Hi, Lid are corresponding loss functions of LEM, HEM, and IDEM. Lambda R is the corresponding weight in loss function. In each part, we build an energy equation E with identity loss and corresponding attribute loss. With the energy equation, we optimize the portraits step by step. We then cascade the subnetworks in this way. The output of former subnetwork becomes the input of later subnetwork. For each subnetwork, we can realize the intermediate results from latent space. Dataset generation. We generate 28 Thorent portraits with CLGAN2. All portraits are labeled with binary tags of length, bounce, and waviness. We generate 3D hair geometry with hairnet. Each geometry consists of 1,024 strands of hair, and each strand consists of 100 controlling points. We then sample color of each point from portraits with 3D hair geometry. Experimental results. This figure shows results in different process stages. You can see that each feature mapping subnetwork only focuses on corresponding attribute without manipulating other attribute. For length, waviness, and bounce, the manipulation on hair attribute is global. The length part changes the total length of hair. The waviness part controls the total hair waviness. The bounce part decides the bounce shape. For geometry and color part, the manipulation on hair attribute is local and focuses on detailed hair strands. The geometry part further fixes the hairstyle, making it more similar to reference. And the color part changes hair color. We compare CFMNet with a turn gun, ST gun, cycle gun, and a Michigan. The three foremost are label-guided methods, which could only transfer coarse-grained hair attributes. Michigan could generate detailed hair with reference images. However, it still needs manual operation on the shape of hair, or else the geometry of hair won't get changed. Results of our method look natural and better match the reference hair. We do also compare FID score with other methods. We achieve the best FID score, which shows generated images for our work are more similar to the dataset. To draw the necessity of Coarse-to-Fine architecture, we obtain examples of different transferring stages. Cgfms can manipulate attributes of large scale, but it fails to transfer detailed hair attribute. Despite the hair color, FGFMs further manipulate detailed hair attribute. This achieves our purpose to dedicatedly manipulate hair attribute. To evaluate the necessity of identity loss, we make the ablation study. Without identity loss, the color on face and shape of mouth is changed. This improves identity loss is necessary in our work. Conclusions. We propose a novel method to delicately manipulate hair with identity preserved. We introduce 3D hair model in our method to manipulate hair in a fine-grained way. Without a tedious manual operation, our work directly transfers hair attributes according to the reference image. Thank you for your attention.